Alright, got some questions this morning. Take out the glasses. So, got a lot of questions this morning, so I'm going to start working through them. If you got questions, put them up in the chat. These all are all organic too. So we'll start with me bringing it up first. Actually, let me just make a little list of these so I don't have to keep hopping back and forth. 14, 16, 17, 20, 22, 26, 27, 28, 30, 31, 34, 35, 48, 53, 55, 57, 59, 62, 65, 67, 68, 69. Not quite sure where the confusion would have come on that many, but we'll start working through it. So, question 14. Select two green agents that can be used to prepare 2-hexanol. So that's our 2-hexanol. We can either view it as, so basically this alcohol would have started as some type of carbonyl group. So we have the carbonyl going left, or the carbonyl going right. And then our Grignard would have been the other half, so GBr or ethyl bromide. So we can do, they're doing, well, okay. So this is 1, 2, 3 butyl, 4 carbon, Grignard. And then I'm going to guess the CH3 MgI is one of them. I'm not sure why they're using I instead of bromide, but let's see. So yes, those are the two that can start. Basically, this started out as a carbonyl. You can either put the carbonyl over here and have this be the Grignard, or you put the carbonyl on this half and let that be the Grignard. Draw an alkene that is formed from 2-pentene by cross-olefin metathesis. Oh good, they're doing olefin metathesis, although I think it's odd that it's including olefin metathesis in this chapter. So I'm going to go on a limb here and guess that this was not the original product, the original one. 2-pentene, 1, 2, 3, 4, 5. In terms of cross metathesis, you can split them. And so you would get that from that fragment. What an odd question. We're going to get rid of 16 because that is not the original question I assigned for that problem. So 16 is actually an olefin metathesis problem. Off the bat, I don't agree with them. I say this as someone who did olefin metathesis research for 4.5 years. Your answer is not correct. (17). The product of the reaction, click and draw the structure below. So this is an, oh, okay. So what you're seeing here, this is the Grubs Catalyst. Okay, so this is actually a real organometallic catalyst. That cross metathesis one is weird. So with metathesis, this is actually ring closing metathesis, RCM. And I'm just going to put an R here because there's a huge group there. So with ring closing metathesis, what we're doing is, the name implies, is that we are making a ring. And we're going to do this by, with metathesis, what you do is you clip the double bonds and then you restaple them. So we're actually going to clip this one to this one. So we have 1, 2, 3, 4, 5. Sure, I'm right about 1, 2, 3. So this is going to be a 5-carbon ring when we get done. And so benzene ring sticks around. 2, 3, 4, 5. And so with this ring closing metathesis, what you're getting is basically take the double bonds, clip them, and then these two ends are going to connect. We're going to get ethylene off. So the driving force here is the free energy of the translational energy of entropy. And we have to just count the carbons in the ring. So we have 1, 2, 3, 4, 5. So this will end up creating a 5-membered ring. 1, 2, 3, 4, 5. With this and this carbon now being double bonded. So that's why I've got my double bond drawn here. And that's what the key shows. So olefin metathesis, this got the Nobel Prize way back in the mid-2000s. It is a good reaction to know. It's actually part of the reason we can make certain types of plastics, certain types of polymers now, as well as certain pharmaceutical drugs. But the big thing with metathesis here is seeing that what you do is you clip the double bonds and then reattach them. So that was 17. Let's look at 20. Draw the principal product from the reaction of 1-bromopropane with lithium diethyl ether. With lithium and diethyl ether followed by copper 1 iodide. Click the draw structure to begin drawing. So we have 1-bromopropane. Diethyl ether. The lithium here is going to basically do what it does with chlorine. So we're going to swap it off, and then followed by copper iodide. This is going to give us the dicuprate. So yes, with the lithium, basically it's saying lithium, and it's weird because your book talks about using chlorine. This is one of the big issues of McGraw-Hill is that they don't always agree with their book. So yes, the first thing you do is generate the lithium complex. So you would just write that in there. Instead of a carbon, it would be an Li. And then with the bromopropane, sorry, actually it's not I2, it's Li here. But you end up getting the double product, or the dipropyl groups attached to the copper. And then you would use this to attach this to another carbon. You use this for carbon-carbon coupling. Particularly, you would use this if you wanted to attach it to the least substituted carbon. So with Grignards, you typically attach the most substituted carbon or the most hindered carbon. They prefer something analogous to like an SN2 pathway. With these organocuprates, they prefer something more like primary or secondary attachments. 22. All right, very simple one. What's going to kill you on this one is just the stereochemistry, because it's going to nitpick you, and it should, but it is going to be kind of nitpicky about how you draw this. So this is the Simmons-Smith reaction. With the Simmons-Smith reaction, you use this CH3I2 and zinc copper amalgam and diethyl ether to create a cyclopropane. The big thing here is keeping your stereochemistry right. So your CH2 group is going to pucker up, so you're going to have a wedge here, and your two hydrogens are going to be pushed back down. So your hydrogens are going to remain cis, and these bulky groups are going to remain cis. Now it's in the key, it's drawing these. This cyclopropane ring is a solid, and saying that this is wedged and these are dashed. It should accept both of these answers, but if you're getting issues where you're still drawing the cyclopropane and it's saying it's wrong, it may just be nitpicking you in terms of like it wants the cyclopropane ring to be solid lines and it wants these carbons to be wedged and these hydrogens to be dashed. You shouldn't need to include the hydrogens in this drawing as well. It should recognize that they are not, they're there. So really the only things you would have to include are these two wedges, but you're definitely going to have to include stereochemistry with this one. 26. An unknown compound molecular formula C7H14 was treated with sodium borohydride in CH3 to form compound B. Molecular formula C7H16. Oh, that makes sense. Compound A has a strong I absorption. 1716 compound B has a strong absorption at 3600, 3200. The 1H NMR of A and B are given. Match structures A and B to their formula. So that 3600 wave number, we've created an alcohol. Sodium borohydride is a reducing agent. It will convert ketones and aldehydes to alcohols. So what we need to consider here is, so it's giving you options for starting and final. So if we look at the 1H NMR of A, the starting compound, there's only 2 NMR chemical shifts, and one's a doublet, and one looks like it's a complicated pattern. Oh, it's a septet. Excuse me. So let's start with the ketones they give you. Well, let's start with the compounds they give you. So on my end, it gives me 4 ketones, actually. Four ketones and 4 alcohols. So actually A is pretty easy to identify, and this is kind of the nice thing about NMR. You need to be able, with NMR, to be able to predict what your compound should give you in terms of the NMR spectra, and match it up to the spectrum you're given to see if it's consistent. So the nice thing about all these, so these 2 right here, these should both produce singlets because these are isolated methyl groups. You don't see a singlet in the 1H NMR. So off the bat, these 2 are incorrect. They cannot be compound A because they should contain a singlet, and what you see in that structure, what you see in that 1H NMR does not have a singlet. So this brings us to this one. So for this one, this would be a triplet, this would be a triplet, this would be a quartet plus a triplet, and it's symmetric, so we'd actually expect to see 3 peaks in the NMR. There are only 2 peaks in the NMR, so this one's gone. This one, this would produce a doublet on these 2, and this would produce a multiplet or a septet. Because of the 6 here, that would give you 7 to give you a septet. So off the bat, for the 1H NMR of compound A, I know that this is the correct answer because it's the only one that these 2 produce doublets. This would require 3 peaks. There are only 2 peaks. 2 peaks here, 1 here for this signal, 2 here for second peak for these hydrogens here. And this is the only one here that would give you a doublet, and that doublet would come from this 1 hydrogen here, and then this kind of septet coming from these 6 hydrogens here. Now that I know that this is the compound I'm interested in, if you take sodium borohydride and reduce it, what you end up getting is this compound here. So is an NMR-B consistent with it? Well, you still got your, let's see here, you've got a doublet. So your doublet about 1 ppm would come from this hydrogen, so this is your doublet, being split by these 2 single hydrogens. You're going to have a singlet. The singlet is definitely going to come from the OH. What happens is the OH pops off faster than the NMR measurement, so it doesn't really participate in J coupling. You've got a multiplet. Your multiplets are going to be these 2. And then, why is it claiming it's a triplet? Or why does it look like a triplet? I'm sorry. Oh, I know why. Actually, these are your doublets still. You're getting a triplet here. The reason you're getting a triplet is because the 2 hydrogens and they have the same chemical shift and the same bonding environment, so they have equal J coupling. So even though it's not 2 hydrogens, there are 2 hydrogens that look equivalent, so it would split at equal amounts. Basically, you're getting a doublet of a doublet, but because they have the same J coupling constant, it's going to look like it's a triplet. So I would say for this one, the easiest one, start with the reactant, prove what the reactant is, and then what you'd expect this to form with sodium borohydride. The other ones it gives you are all the reduced forms of the other ones. They should all contain a massive singlet. Actually, they should contain 2 singlets, one for the alcohol and one for the methyl groups. So the ones I drew earlier that had the 3 methyl groups, those are automatically off the bat wrong. And then the dipropyl ketone, that also should produce 1, 2, 3, 4, 5 signals. You're only seeing 4 signals in that compound B, so you can definitely discount the reduced form of that dipropyl ketone as a candidate because it's got way too many. It would have way too many peaks in its NMR spectrum. Okay. (627). This is same type of question. So you got a treatment of compound C, molecular form is C4H8 with a Grignard followed by HO, which affords compound D. Molecular form is C10H14O. Compound D has a strong peak and SIR peak at 3600. That implies it's an alcohol. And the 1-HMR spectrum C and D are given. Match the C and D with their with what they are. So let's start by identifying compound C. You're reacting with the Grignard, so you're going to need something that would react with the Grignard. The alcohols are not candidates here. What they tend to do is deprotonate in the presence of Grignards. So we've got this, 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 and this one here. And if we look in the 1H NMR, we have 2 singlets, one with area 2, one with area of 6. Now in practice you reduce this to 1 and 3, whatever. It's 2 singlets. So when you look through our compound, our starting ketones, or starting compounds here, and see which ones would have reacted with, which ones are consistent with a 1H NMR. This isn't, because this, and this are all not singlets. That's gone. This has a singlet here, but that's going to be a quartet. That's going to be a triplet, so that one's gone. We've got singlets here and the singlets here, so this is a candidate. These are going to be doublets, and this is going to be a septet, so this one's gone. So just by looking at the 1H NMR compound C, there's only one possibility here, and it's this. It's this epoxide. So it looks like the C6H5. So at least on my end, it's pairing up the those ketones and aldehydes with what would happen if they reacted with their Grignard. In all cases, this Grignard you're adding here is you're adding a benzene ring. So there's 2 positions where we can add this benzene ring in the and with this starting reagent here. We can add it to good. It's actually giving you multiple answers here. We can add it to the left or to the right. So if we add it to the left side, versus adding it to the right side. So if we look in the 1H NMR of compound D, we have 1, 2, 3 singlets and a multiplet. So that multiplet buried down about 7 to 8 ppm, that's your phenyl ring. So in all cases, that's your multiplet. So what we need here are a whole bunch of singlets. Now one singlet's going to come from the alcohol, so we can automatically say like one of these is a singlet. So now if we compare these 2 different options, this will produce a single singlet, so we'd have just 2 singlets. Actually, you still have 3 singlets here. Did it give you a second option? Oh, it didn't. It only gives you 1 option for the epoxide. Okay, so this problem's even easier. Okay, so if you compare the predicted structure of a Grignard attacking the epoxide, only one of these works out to be correct. And it's the one that looks like that. So I made this problem way harder than you had to because I was looking at both left and right because it doesn't specify acidic or basic conditions. Actually, there's only one compound in this list that would look like the epoxide after it got attacked by the bromobenzene, the Grignard benzene reagent. So this is another one. It's a lot better to start with the starting reagent, figure out what it is, and then predict what you expect to have and make sure it's consistent with the NMR. So 28's the same way. I would really just highly encourage you to go through and look at the starting NMR and try to figure out what the compound is. That peak at 3600 implies an alcohol. The reason they're making the alcohols, it's super easy to characterize their NMR. So you can definitely use the IR to figure out what the starting compound is in terms of its structure. But I would definitely rely on the NMR. It looks like you got a singlet and a doublet or triplet and a quartet. That should be pretty easy to tweeze out what that is. But yeah, for 28, I'm going to say go through and do the similar kind of analysis of going through and saying, okay, the starting compound E, what NMR is consistent with it, and then based on how the Grignard would have added to starting reagent E, what is the most likely product, and that seems to be how these problems are working. 30. Draw the structure of isomeric alcohol that can be paired by lithium aluminum hydroxide with reduction of a ketone. Okay. Sorry, just checking the key to make sure I'm approaching this the right way. So all it's asking you is if we just have a ketone of the form C5H12O and we reduce it with lithium aluminum hydroxide, what are we going to get? And so when it's saying isomeric, it means that we're going to ignore stereochemistry here and just draw it. These are all basically constitutional isomers. So for C5, 5, this is a ketone possibility, this is a ketone possibility, this is a ketone possibility. There's really not anything else you can do. Everything else would be an aldehyde. So if you did the linear and you put the carbon on the end, that would be an aldehyde. For this one, you can't put a ketone here, so this is the only possibility. And then if you just reduce these with lithium aluminum hydroxide, these would be the different alcohols you could produce. And again, it's telling you to do the isomeric. It says it's not really caring about like the stereochemistry. You would get RNS here, RNS here, RNS here. But those are your three possibilities. So carboxylic acid is going to work the same way. It's actually going to be the easier problem here. There's only a handful of carboxylic acid you can draw. So we have the linear one, because carboxylic acids all have to appear on the end. We can put a branch here. We can put a branch here. We can put a branch here. And lithium aluminum hydride completely reduces carboxylic acids down to alcohol, so we're just going to get rid of that double bonded O. And these are all your different possibilities. (34) Complete the chemical equation for the preparation of 2-butanol through the use of a Grignard reagent. So it wants to know what you're reacting, what compound 1 is to make this. A Grignard is always going to add to some type of carbonyl carbon. And in this case, we're adding a CH3 group. So this is our carbon. We added a CH3, so this is going to disappear. this is going to turn back into a carbonyl, and that's what you're starting with is pentanal. Um, 35 is the exact same line of reasoning. You're going to cut off your Grignard reagent, and wherever it attached, that's where you're going to get that's where you form your alcohol. Wait, I'm a bit confused, but hold on, let me look at 35 again. Complete equation showing how 1-phenyl ethanol can be prepared from, acetophenone. Gotcha. Okay. Sorry, I thought this was another Grignard problem. So you're starting with this compound, and I'm just going to use a pH here for the phenyl, for the benzene ring. And it's giving you this is the starting compound. It wants to know what you would do. This is a reducing agent. It's increasing the oxidation state of carbon. So your reducing agent here could be anything, but you are reducing carbon to give you this. And it wants to know what can do this. Osmium cannot. Chromic acid cannot. Chlorite cannot. PCC cannot. Potassium permanganate cannot. H2PT, yes, you can definitely reduce it with that. Magnesium chromate, not happening. Sodium borohydride, yes. Lithium aluminum hydride, and I don't think the silver nitrate is going to do it. Yep. So anything containing chromic acid, so PCC, CrO4, Cr2O7, definitely not a reducing agent. Osmium, those high oxygen compounds are definitely not reducing agents. And I'm not sure what silver ammonium nitrate is. That may be Tollens reagent, but Tollens reagent is an oxidizing agent. 35, 48. Draw the product form from oxidation of HCOH with periodic acid. So periodic acid likes to cut double bonds, and I think it forms ketones. But there is a reason why it's giving you this symmetric alcohol. Yep. So you got ethylene glycol here. What happens with periodic acid, HIO4, perchloric periodic, is it basically cuts your double bond and turns it into carbonyl. In this case, we have two hydrogens sticking off that carbon. So in this case, we're going to get formaldehyde from splitting the ethylene glycol. 53. Complete the following equation by drawing the structural formulas for compounds A through C. So a big thing here is keeping an eye on chemical formulas. So our starting compound here, cyclopentadiene, C5, it would be 12, 8, 6. And we got C5H7Cl. This is going to imply that we're making, we're just doing a single addition. You can get kinetic or thermodynamic products. So let's just start with kinetic product first. And sodium bicarbonate is a base. So now we're at C5H7Cl. C5H8. What are you doing? Because definitely the last step is chromic acid. So C5H6. Let's work backwards. So C5H6O. 1, 2, 3, 4, 5. So there's my 5. There's my oxygen. I have 6 carbons, 6 hydrogens. So that's my final compound. So here, the bicarbonate is a base. It's just promoting, it's actually an acid. This is a weird thing to write. Bicarbonate is both an acid and a base. So what's happening with our, basically our bicarbonate is serving as an acid source. So you're replacing this with an oxygen. So working backwards, okay, you got C5H6O. That chromic acid tips you off that it was an oxidation probably of alcohol. So these are alpha beta unsaturated ketones, pretty stable. They're actually the desired end result of a lot of reactions we'll talk about on the next exam. But your C5H6O here, this is your final compound. Working backwards, you reduce it from the alcohol, and this HCO3 here is an acid source with H2O. This is just going to be an SN1 or SN2 reaction to get rid of the chlorine. So the first thing that we do, add the HCl, we're going to get the kinetic product, and even if we don't, you can't tell the difference because of the thermodynamic product. It's just going to have it rearranged. You're going to swap out the chlorine with an alcohol and then oxidize the alcohol to give you the alpha beta unsaturated ketone. 55. Draw the structure of the principal organic product formed from the reaction of one propanol with the following compound in the presence of pyridine. So this is just tosyl chloride. So TSCl will replace the alcohol. This is what we use to draw. So this is actually Chem 251 review. So that big compound here, this is called tosyl chloride. This is actually used to react with alcohol. So what it does is it takes the hydrogen off the alcohol. And so for one propanol, you would end up getting this tosyl propanol. It is a beast to draw this out in the software, but that's all it is just a big big compound like this. The reason you want to do this is that you would want to do you want to guarantee an SN2 pathway. So if we had something like chloride here, chloride would pop the oxygen off and we were guaranteed not to get carbocation rearrangement. In terms of what they form, para-toluene sulfonates. It's going to come to questions about chromic acid. And it's weird because the chromic acid last semester did that for us in South, and apparently it's gone bad. I'm not sure what's going on with our chromic acid on South Campus because it is not aggressive at all. So I'm guessing it hasn't been made up correctly. 57. Draw the structure. The following reaction has been performed in chemical order. Draw the product showing the proper stereochemistry where relevant. So chromic acid here is just a really good oxidizer. So we got this, OH, 3, CH2, CH3. So that's your starting compound. So there's your CH3, CHOH, C triple bond carbon, CH2, 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 CH3. Your chromic acid is just going to convert this to a ketone. '59. A diol does not react with proiotic acid. Its 1H NMR is shown below. Draw the structure of this diol. So we have C8H18O2. And it's highly symmetric because we have 2, 4, and 12. And it looks like a lot of singlets are buried in there too. Honestly, I don't like this question. Probably was a lot simpler on my end. So I'll get rid of question 59. I'm not a huge fan of what they're asking there. So questions 16 and 59 I'll get rid of. 59, that's just a little too hard. 62. Okay, 62. Treatment of compound C with this followed by forms compound D. I've already answered 2 questions like this. In fact, I think this is actually a repeat question. So yeah, it's the same approach. You need to go through and figure out what the starting compound is, and then figure out what it would make. Based on, once you know what the starting compound is, look at what the Grignard would make. 65. Choose equation describing different ways in which benzyl ether could be prepared by Williamson ether synthesis. So Williamson ether synthesis, what you're looking at William ether synthesis is that you have an alkoxide, so an alcohol reacted with sodium, reacting with an alkyl halide. So the one that has sodium metal bound to the benzene ring, definitely incorrect. One that has the bromine bound to an oxygen, definitely incorrect. And so that leaves us down to 3 possibilities. Actually, so on my end, the first one has the sodium bound to toluene, definitely doesn't work. The second one has two alkoxides, doesn't work. Third one has an oxygen bromine bond with sodium bound to a carbon, that doesn't work. The fourth one has bromotoluene, so it's got the bromine attached to the CH3 group, CH2 group, and an alkoxide, that would definitely work. And then I have another one where it's a benzyl alcohol alkoxide and ethyl bromide, that would work. But a lot of these are kind of like, you can't make these compounds, so you really can't have sodium attached to carbon, you can't really have bromine bound to oxygen. At least not with the types of compounds we work with. 67. What is the principal organic form from the reaction of ethylene oxide with sodium cyanide and aqueous ethanol? This should be a pretty easy question. That one finally died. This is just nucleophilic attack. So you'll get the nitrile. So that's just a Chem 251 review. 68. Which the following principal organic products form from the reaction of ethylene oxide with phenyllithium and diethyl ether? It's the same type of problem, but instead of having cyanide as your nucleophile, you've got this compound instead. And do keep in mind, so I interchange benzyl and phenyl. I really shouldn't be doing that. They are different compounds. So phenyl is this. Benzyl would have been this. So for the phenyl, we're getting an attack. The oxygen bumped up. If we were asked to do benzyl, we would have the carbon on a toluene doing it. But it's the same idea. You've got nucleophilic attack on an epoxide. What is the principal form of ethylene oxide with 1-butyl sodium? Again, it's the exact same reaction. You're just changing what the nucleophile is that's attacking the benzene ring. So that's it for that list of questions. I've got the chat open in case you've got any questions, but make sure that move that out of the inbox. So I've got the chat up if you got any questions. Otherwise, these are just office hours. These aren't lessons. These are lectures. So just chime in if you got questions. All right, had to finish responding to an email, but I got a question. Can you explain the Heck reaction? So the Heck reaction is going to kind of be our first introduction to more of the named reactions that show up a lot more in organic too. For a lot of these, we do not concern ourselves with the mechanisms. The big reason being is that the mechanism is not well described under Lewis theory. It actually requires an understanding of inorganic chemistry to explain what's going on. So the note's talking about how generally start with this R1X. So X in this case is typically bromine, and we're going to react it with some type of terminal alkene. And the catalyst here is a palladium acetate. And what we generally get is basically our substitution onto the N in the trans form. So what we should get is the trans alkene. Although occasionally we can get substitution here. This is unlikely, and the big reason it's not likely is because of steric hindrance. So the nice thing about the Heck reaction is that it pretty much takes the terminal alkene and starts stapling to the ends of it. We don't have to worry about, like, we will get some minority product where R1 gets added to the other side. Again, we're clipping off a hydrogen and putting the R1 group in its place. There's devils in the details in terms of where the hydrogens get clipped off, but this is why we're going to stick to the terminal alkenes. The most common application of this are actually bromobenzenes. My background is not with the Heck reaction, so I'm not 100% sure what it's used for, but it is actually, based on what I was able to find out about it, a pretty useful reaction. But in all cases, if we have some type of terminal alkene, particularly one that's got some bulky groups beside it, what this will do is it will just basically clip off a hydrogen, clip the hydrogen bond and the bromine carbon bonds, and reattach our desired group here. And we should be able to do this with pretty much whatever groups we want to, but particularly with a benzene rings, it has to do, I don't want to say this. The only rule here is the bromine has to be attached to a double bond, and this has to go through the details of the mechanism that, again, we're not going to go into depth in terms of the depth into why. But if we have any situation where bromine is bound to a double bond, what we effectively do is just cut the bromine carbon bond, a hydrogen carbon bond, and we end up with this final product. So it's a very nice, very elegant carbon coupling reaction. The big reason we would want to do this practically is because this palladium acetate, these are pretty gentle conditions to make this happen. So we're not having to go to really far extremes to kind of promote this chemistry. Like, we're not having to run it under like high temperatures, high pressures, or air free. I'm not sure if that quite answers your question. But again, the overall picture of a Heck reaction, we have bromine attached to some type of double bond, and we have a terminal alkene. And what we're going to end up doing, clipping these bonds, connecting these carbons together. And it is very selective towards the trans isomer. There is an exception that's kind of shown in the notes where if you do like ring forming, it will actually like do the cis if the cis makes it more stable. Don't know if that answered your question though. Gotta ask, does it matter which group attached is up or down when it's trans product? So, I'm not quite understanding your question. So let's take our very simple terminal alkene here. And when we do the attachment, we're going to have R4 here. And then we're going to have attachment to the double bond. The only rule is that whatever is attached to this bromine, so the relative connectivities here have to stay the same when we do the bond. So we have R1, R2, R3, but this is a carbon-carbon single bond, so we can engage in rotation. And when we do the rotation, go to R1, R3, R2. So practically what would happen is we would get the zigzag conformations to make sure everything's eclipsed. But as far as like the double bond pointing up or down, that doesn't really matter because we have this carbon-carbon bond single rotation. Again, the only rule here is that however these were connected relative to bromine, that's how they need to be connected relative when we get a relative in the final product. So if it was on the same side as bromine, it needs to be on the same side as where bromine was in that bond. If it was cis, if it was trans, those relative geometries have to stay because we're not rearranging the bonds in here, we're rearranging the bonds in here. So hopefully that answered your question. All right, so that's in for office hours. Again, if you have questions, please feel free to email them in advance. And I have in-person office hours on Fridays from 9 to 11 if you need to come in person. Otherwise, I will see you all tomorrow.